in the Department of Computer Science at Bowie State University in Maryland, USA. And I'm here with my colleague, Temitope Oyemade, and we'll be presenting on the topic analysis of synchronization mechanisms in operating systems. Okay, so for introduction, the study of synchronization mechanisms has, become increasingly important due to the growth of new, modern operating systems in our computers. And so synchronization helps to ensure that concurrent processes or threads access, shared resources in a controlled and orderly way, so that it can prevent, issues like race conditions and data corruption. So what are concurrent processes? Concurrent processes are, multiple, it's like running multiple independent tasks or programs, at the same time, like executing programs at the same time on your computer system. And in concurrent executions, the multiple processes or threads, share resources such as the memory, the file, CPU time, and therefore, because of that, we must avoid issues like data corruption, deadlocks, or, race conditions. So now the question would be, what are deadlocks or, race conditions, so that we can appreciate, the importance of synchronization methods. So a deadlock is basically like a situation in concurrent processing where two or more processes are unable to proceed because each process is waiting for a resource that the other process holds. A typical example is, for instance, let's use like a traffic, and only one car can, pass at a time, but then two vehicles try to pass at the same time. So, it's going to block the entire traffic, causing a gridlock. And so if that happens in your system, everything is just going to shut down because nothing is happening. And then race condition, on the other hand, occurs when, two or more processes or threads access shared resources simultaneously. And the final outcome depends, on the timing of their execution. So it's like processes are racing, to acquire a shared resource. And a typical example is like, let's say someone issuing a check, $100 check to two people, and the person only has $100 in his account. So those two people are like racing to cash the check. And it is important, for the system to be able to order the process of cashing that check. So if the both of them present the check at once, and let's say two different cashiers click withdraw at once, and there's no condition to make sure one waits for the other to process, then two people will have $200, leaving, the bank to have to settle. So that's just like to give you an understanding of what race condition is. So this research, evaluates the performance of what we have, decided it's the four most common synchronization mechanisms, which are reentrant locks, semaphore, synchronized methods, and synchronized blocks. And we're analyzing them by running them on three major operating systems, which are Mac operating systems, Windows, and Linux. And so the objectives of our research to review and evaluate existing synchronization mechanisms, which, are so many, and the tools that, these mechanisms use in modern operating systems. So in our literature review, we reviewed several papers to know the synchronization methods that are commonly used. And from there, we selected the four I just mentioned. Also, the study aims to assess the performance of these four mechanisms, which are reentrant locks, semaphore, synchronized methods, and synchronized blocks, under different system configurations, Those are the three operating systems, Mac, Windows, and Linux. And after, assessing this performance and getting our test results, we analyze the variability in performance across these platforms. And so for our hypothesis, after we did, the in-depth literature review, I think we reviewed about 30 or so, and we hypothesized that synchronized block and synchronized methods are likely to be the most efficient mechanisms based on the popularity, because it seems, most of the researchers or most of the studies use those two. And it is worthy of note that synchronized methods and synchronized blocks are mutex-based mechanisms. So, and then as a result, we hypothesize that reentrant locks would be less efficient since it wasn't as widely used as the rest. So yeah, and this table shows the more like the findings from our literature review, and we would see that the mutex lock algorithms, that's synchronized methods and blocks, are like the most popular, and then followed by Semaphores, reentrant locks, and the rest. So we chose to analyze those for the first four: synchronized methods, synchronized blocks, Semaphores, and reentrant locks. Okay, so for our methodology, I'm going to hand it over to my colleague, Temitope, to take it up from there.
Hi, good evening from here. My name is Temitope. I'm a master's computer science student here at Bowie State University. And we are partnered with Toyin to be able to come up with this paper and also do this research. Okay, so I'll be speaking on the methodology, the approach we used in carrying out our experiment based on our research. So putting into consideration the four types of synchronization and mechanisms that we are talking about in this context. So for our methodology, we ran our experiment on a computer M1 chip processor, a Mac M1 chip processor. It has like a 16 gig of memory, of RAM, and also we had a virtual we had other operating system running via parallels virtual machine. So we tested 10 threads, we created 10 threads at the same time, and we executed this operation 1,000 times to carry out this experiment, this test, so that we can be able to determine, based on this hypothesis, we're able to determine which one has the best performance across different operating systems, across all the four types of synchronization mechanisms under consideration. Can move to the next slide. Okay, so starting off with Semaphores. So basically, the way we tested Semaphores was, okay, so basically for this project, we used Java. Yeah, we used Java. So for Semaphores, Java util class has has a package for semaphore. In Java util concurrent, you have a semaphore class in there that comes with out of the box implementation for acquiring a log and also releasing a log in Java. So what we did is the approach was, we had an interface where all of these four, so we created 4 different implementations for different types of synchronization and mechanisms that we're considering. So we had an implementation for reentrant lock, we have one for semaphore, we had one for synchronized method, we have another one for synchronized block. No, now for semaphore. Semaphore, because semaphore is it's a class that has already existed in Java, the concurrent class. There wasn't a point for us to start creating it again out of the box. So we just reused the semaphore class in Java. We created a shared resource, and we created 10 threads to be able to like access the same resources, and we use semaphores to obtain lock and also release the lock as the case may be. So basically that was what we used to with, for semaphore, there's an acquire method and also there's a release method. So before before we access our shared data, we acquire the lock, and also when we are done, we release the lock. So this was kind of like in a try and finally block. So we try acquiring the lock. If a lock, like if a thread already has access to the lock, then we won't be able, the second thread will not be able to access that lock. And eventually when the whole process is done, in the finally block, the semaphore like releases the lock. So that has covered like for both semaphore and reentrant lock. Then can I move to the synchronized block section? So the synchronized block section is slightly different, because synchronized block basically is just the static block in Java, whereby you can just create like a synchronized block, if you know what I mean. Like it's a static block whereby it just contains some special kind of code. Yeah, like it has to be you are trying to log into it, and perform all your actions in that block. However, this has a limitation, because, for example, if the application that you are trying to that you've implemented this login is based on like it's deployed on multiple servers, like it has multiple instances. So, for example, it's deployed using Docker, and you have like different containers running at the same time. If using this approach limits you, because what has been acquired in the first container, the second container will not be aware of that same resource that has been locked, especially if that resource is like a database resource. So that's for synchronized block. And also moving on to the next one, a synchronized method. Basically, all you just have to do for a synchronized method is still on the same tags of shared resource. You just have to like add like the synchronized keyword to your method if you are trying to like implement synchronized method in Java. Yeah, so like those are some limitations of this approach that we had. If you're running multiple instances, I'm afraid like you might not really get the best out of it, except maybe you are sure that okay, your application is running, it's a monolithic application that is running on a single instance, and the resource they are trying to manage is just in that particular instance where you are running your test on. Okay, over to you, Toyin.
Okay, thank you, Temitope, for that. So now we're going to analyze the result of our test. And so for the result, we have like the raw result, which is, basically just a simple average of, all the tests. As we can see, like the average of running this synchronized method on Mac 1,000 times, 1,000 times on Windows, and 1,000 times on Linux, and that applies to everything. So for that, we would see that reentrant logs, this is reentrant logs, and it exhibits the lowest across all platforms. Actually, it exhibits it's 14 on Mac and on Windows, and then it's about 16 on Linux. But for the other ones, they were fairly stable, because for synchronized method, it's just 1 millisecond difference. Here also is just 1 millisecond difference, and here it's also 1 millisecond. So if we just look at this alone, we would conclude that reentrant log is the most efficient. We would say it's the fastest and the most efficient, which actually contradicts our hypothesis, because we had said, based on how common and how popular the mutex methods, which are the synchronized methods and blocks, we thought, oh, maybe people are using it because it's quite efficient. But then when we go to further analysis, so we decided to do some statistical analysis on that raw data. So for the averages we got, so let's say for the 16, and 17, we got the mean, the standard deviation, and the variance. This is what we have for all the four mechanisms. And so looking at a graph, we would, let's look at reentrant log first. You'll see that, okay, yeah, it has the lowest mean, which, actually means that, yes, it's the fastest, generally on all platforms. Reentrant log is the fastest. But then if we look at the standard deviation and the variance, we see, across all four, it has the highest. So it means, it can't really be predicted. It has a lot of variability across, the three operating systems. But then for the other methods, synchronized method, synchronized block, and semaphore, although they have, high, the time it took, the execution time is high, but they're fairly stable, looking at their standard deviation and their variance. They're fairly stable across, the different platforms. So yeah, well, this is what I just discussed. And so what this means is that we believe that the higher variance observed in the reentrant log's performance may be due to platform-specific optimizations or inefficiencies in handling thread scheduling and all of that. And, on systems like Mac, which are known for efficient thread management, reentrant log performed exceptionally well. So we feel the operating system, helped reentrant log. I mean, they kind of work well together. But then on Linux, which prioritizes versatility and customizability, the performance of reentrant logs may have suffered from higher overhead associated with managing multiple threads. So, and then for the trade-offs, we would see that reentrant logs, yeah, are best for high concurrence applications, where the performance is critical. We want it to perform, in a very short time. But, we have to always consider, developers should consider that it's not as predictable for different operating systems. The mutex-based mechanisms, which are synchronized block and synchronized methods, are ideal for applications that prioritize stability and consistency, especially in cross-platform environments. So for our conclusion, the findings of our research is important for system designers and developers, particularly when they're choosing the appropriate synchronization mechanisms based on the needs of the applications they are developing and the platforms that they are working on. Because, and then, okay, also, we would see that, just like I mentioned before, the hypothesis that mutex-based mechanisms would be most efficient was contradicted. Reentrant logs were found to be the fastest, although, it has variability issues. So practical implications for this would be that for application developers, they should consider that for applications where raw performance is critical and where variability in execution time is acceptable, reentrant logs offers the best performance. However, just like I mentioned, you should be aware of the higher variance across different platforms. And for applications that prioritize stability and consistency across different operating systems, they should use synchronized methods, synchronized blocks, and semaphores. And this is especially important, for instance, in enterprise level applications where uniformity and reliability are critical. Okay. Now for future work, there are several areas where future research could build upon or improve the findings of our study. First is native testing across platforms. This study was limited by the use of virtual machines for Windows and Linux. We used the actual hardware for the Mac, but we had to run Windows and Linux on a parallel virtual machine, which we feel could have introduced some performance overheads that do not exist in the native environment. So future work should include testing each operation system in its native environment to eliminate the influence of virtualization. And this, we believe will provide a more accurate comparison of synchronization mechanisms. Secondly, we also believe that if future researches expand the range of synchronization mechanisms. For instance, we just studied 4, and from the literature review, you'd see that, we had other less common mechanisms, which, might be an area to look into. And thirdly, recollect that we used just 10 threads, to run our test, and we, ran the 10 threads 100 times for each mechanism. So future work can increase the load, and this would also be particularly valuable in real-world applications such as databases, or large-scale web servers where thousands of threads may be completing resources simultaneously. Okay, so the implications is that reentrant lock is ideal, for high performance, as we have said, and mutex-based mechanisms offer predictability. And, I guess that tells us that's why it's more popular than the other ones. Okay, thank you so much for your time. Thank you for listening. Are there any questions for us?
Thank you so much for your presentations. Any question from the audience?